a hypothesis be tested by the realism of its assumptions. And the realism meaning then whether the assumption is a somehow accurate representation of a real situation, right? So, and we'll see what's happening here. Okay. And then he argues here with 4 different examples, and the examples also have their intricacies, and also in the discussion they play a major role, and they are really not without problems. We'll see that first. So I told you in the beginning that Friedman claims that economics can be a science as objective as the physical sciences, and therefore it's not absurd to begin with an example from physics, because he thinks what's holding for economics, or what holds from economics methodologically, is more or less the same situation in physics. And therefore he starts with a physics example and then turns slowly to the economic examples. Only the last example out of 4 is a real economic example. So he starts with that example and he tries to show us something in the physics example. And this is really physics, undergraduate physics, or even high school physics. The law of free fall. That's valid in a vacuum, as we are told. Now, okay, so when this law is applied in a situation without vacuum, this is the law of Galileo's law of free fall. So it's from the early 17th century. It's, in a sense, the first law that was discovered in modern physics. Whatever. When applied in a situation without vacuum, the law is good for a falling ball for short distances, and it's bad for a falling feather or bad for a falling ball from high altitude. So if you want to find out how a jumper from an airplane, how he or she behaves without the parachute open, then the law of free fall won't do very good, because they reach a maximum speed of something like 250 kilometers, and then the friction is so strong that there's no free fall anymore. According to that law, they're free falling, but the law doesn't apply. So it wonderfully does it work on a distance of 2 meters or 3 meters with a heavy body, but as soon as you take a feather, then of course it doesn't apply either. So you have a law that has certain conditions under which it works, and under certain conditions it doesn't work. And it's supposed to be absolutely valid in absolute vacuum, right? This is the assumption. So if you have only this gravitational force, then the law is fully valid, and now we are not applying it usually in a vacuum, but in other situations. And the question is then, how can we understand that? All right. So the point is now, when you have the idea, and this is again, it's the title of the section, is it possible to test the hypothesis by its assumptions? When you say we have this situation in physics, that would mean, when we test the law of free fall, would mean that we test whether the actual air pressure is 0 or close enough to 0. Right? That would be the implication. And now he's trying to show us that doesn't work. You cannot do that. Okay. But this is only answerable by investigating whether the formula gives good predictions for particular situations. So if you simply say, is the air pressure in this room close enough to 0 for that law to hold, you cannot give an answer. But what you have to do is, you have to investigate how do bodies fall in that room, and then look whether the predictions of the law are good enough. There's no way of independently saying, yes, air pressure is near 0, because you don't know. Well, the air pressure is not 0, it's massively above 0. I mean, it's 760 something hygrometer. So it's not 0. And the question is whether it's good enough or not good enough. It's a question you can only find out. This is his claim, and he's right there. It's the claim you can only find out when you really measure falling bodies here in that room, heavy bodies, and then you look whether they follow the law of free fall or they don't. And then if they do, then you say, okay, the assumption is justified to the degree that we tested it here for short distances of heavy bodies. So the example illustrates the following. This is what he's getting from there, and that's central to the paper. The impossibility of testing a theory by its assumptions. You cannot say, if I have the law of free fall and I want to apply it here, then I test the law of free fall by discussing and testing the assumptions. The assumptions being vacuum, there is no vacuum, so there is no testing. You can't say that. The only way is the inapplicability of a theory for special cases is only revealed by bad predictions, and an independent test of the assumptions is impossible, right? So the test of air pressure is close enough to zero, can only be tested if you use that assumption in a theory and then you look at the predictions. There's no independent test possible. And that's quite plausible if you look at the example, right? And second, there's an ambiguity in of the expression assumption of a theory. The successful cases of the application of the law of free fall show that in these cases bodies fall as if they were in a vacuum. So you are not claiming when you show that here in this classroom bodies fall according to the law of free fall, you are not claiming then, yes, I assume rightly that here is a vacuum. You're not assuming that. You're not claiming there's a vacuum in this class. You're only saying the assumption, the S is good enough, so the body behaves as if there was a vacuum here. When you use the word assumption, it's usually meant something you cannot prove, but from which you think it is true, right? So I assume for the sake of argument, then it's different. But I assume this and that, and then you say, let's play around with the idea that this is true, right? I assume that. And then you cannot prove it, otherwise you would call it a theorem, or you would call it an empirically verified sentence or something like that. But in assumption, you usually assume of the assumption that it is true, or at least approximately true. But he says this is not the point. It's not the point to assuming that here's a true vacuum, but the point is something counterfactual. And then you say the situation here is as if there was a vacuum. And that's very important because this as-if methodology is also a hallmark of Milton's paper here, Milton Friedman's paper, and it's been discussed many times. So, in economics, when you have such a situation, economists would then talk that it would be translated into the theory assumes a vacuum. And here you begin to see why he says this assumes is not really right? When economists speak that way, because it's not claiming it's true. It's just not claiming the truth of the assumption. It's just claiming a situation is such that I can treat it as if there was a vacuum. And so it's an as-if assumption, and that's not an assumption in the normal sense where you believe it's true. And this is not the case. It's only stated that for some situation, the only relevant variable is gravitational force. So it's only when you say this is an assumption in economics, that would say, oh, that's an assumption, a general assumption that holds in all of economics. Whereas Friedman says, no, the assumptions in economics are very local. They only mean a particular problem situation, and in a different problem situation, you will make different assumptions, right? And you never claim they are true, but you only say, I can treat in this particular situation, I can treat the situation as if the assumption were true, right? But I know it isn't. And I'm not claiming that for a different situation, that's also a good assumption. It's an as-if statement, which is good enough for the situation. This is what he tries to demonstrate here with that law of free fall, and he's going to elaborate that in the other examples, okay? So we start perhaps seeing why he's not happy with that term assumption. And I told you that the term assumptions, I think, occurs 73 times in the paper and 35 or 36 times with scare quotes, because this is not the normal sense of assumptions, and that will become much clearer later during the paper and in my comments then. Now, example 2. So this was the physics example. This he developed just that we get the feeling that this is not, so to speak, abnormal in economics, but you find it in physics already. And now he's moving slowly to something where he says example 2 is an analog of many hypotheses in the social sciences. And when you read this hypothesis, you will say, I don't see the analogy immediately. So let's discuss it. And there he considers the density of leaves around a tree, right? So trees have not always the same density of leaves around them, but it depends where they stand, what the shadow is, what the sun is, and so on and so forth. And there he says, now let's consider the following hypothesis H star, namely that the leaves behave as if they individually calculated maximally receivable sunlight and then moved each leaf individually accordingly. So he's assuming, or this H star assumes, each leaf, calculates where do I get most sunlight. Each leaf does that, and then they can move around on the tree however they want. And this is the assumption by which he tries to get an understanding of the density of leaves around a tree. So if you have a leaf that stands very close to a building, for instance, then at that side there are fewer leaves than on the other side. Or if you have a special shadow, then you have in the shadow there are less leaves than in the sunlight, and then the leaves will typically look southwards and northwards, and so on and so forth. So he's asking the question, what are we doing with that sort of situation? And then he says, what we do in the social sciences in parallel situations, we do something like this hypothesis H star, which is absolutely counterfactually, right? It's absolutely idiotic. Neither do they leave calculate, nor do they move individually, nor anything. They're just sitting there, and waiting for the sun, right? And what's the argument? What he's saying is that some consequences of H star, of that crazy hypothesis, about calculating leaves that move around individually, that some consequences of H star are consistent with experience. For example, that leaves are usually denser on the south side of the tree. So he's introducing this completely counterfactual, absolutely counterfactual hypothesis H star, and says, look, but it makes sense insofar, qualitatively consistent with the consequences of that hypothesis, consistent with experience. So many people, of course, reading that would say, come on, why don't we talk about economics, right? Talk about economics, please, and not about artificially constructed examples like this tree stuff. But he's got a good reason why he does it, because that will make transparent the point he's trying to make. Now, H star is obviously false, quite obviously, no discussion, but it has, he puts it, great plausibility. And I don't know whether plausibility is the right word. I would rather prefer the word validity. That's possibly a better word, but I don't want to quarrel with him about the word. He says great plausibility because of the conformity of its implications with observation. So he says it has great plausibility because of the conformity of its implications with observation. So he's saying that's a sort of argument here. He says, use this H star, this crazy hypothesis about leaf distribution. Why? The argument is because the conformity of its implications, not the hypothesis itself, but the implications. So if you look at the implications of the hypothesis, then you get qualitatively, for many occasions, you get the right results. Namely, for instance, leaves concentrating more in the south than in the north, etc., etc., etc. Right? This is the argument, right? So he says the introduction of a completely contrafactual hypothesis, or assumption in that case, is somehow justified because of the conformity of the implication with observation. Right. So, now, the validity of H star, this is what he claims further, may be explained by showing that its consequences are the same that those of a much more realistic hypothesis H, embodying passive adaptation of the leaves. So if you ask the biologist or the botanist in that particular case, how come that the leaves are distributed on a tree as they are, then he says, or she says, the botanist will tell you, look, this is an adaptive feature, and those trees that make optimal use of sunlight, they've been selected in the history of evolution, and therefore what you find is you find a certain optimality of the leaf distribution on a tree due to the process that led to the existence of that particular leaf, a particular tree, namely selection processes in evolution, right? And therefore you can say, oh, if there is an optimization process in nature by a selection process based then on mutations and other processes in evolution, that may be, so to speak, modeled or emulated by a process as if the leaves themselves decided what's my optimal place in order to get maximal sunlight. So this is what he's saying. So this is the validity of H that can be explained in this way. And then H is to be preferred not because of its higher realisticness. So this is also very strange at the first moment, isn't it? You know, you shouldn't prefer H, so the real evolutionary explanation for the distribution of the leaf, because it's more realistic, but he says, because it's part of a highly confirmed, more encompassing theory, namely the theory of evolution, which supports H. So if you say, why do I like H better than H star, it's not the realisticness is the most important argument, but it's the argument that it's embedded in a bigger theory. So it gets theoretical support from the theory of evolution, whereas the other theory, this counterfactual theory, is not embedded in such a theory, but it somehow only emulates the result of selective processes in the theory of evolution. And then quite clearly, he also stresses that H star is only valid for a class of very special situations. Right? Only for trees in a certain situation, this is valid, then you get the right consequences, right? So if you do something to the tree, so you change the sunlight daily or whatever you do, then the H star may give you very bad predictions, but in certain situations it may give you very good predictions. This is very important. He stresses it again and again and again. In economics, you always have hypotheses that are tailored for certain situations and certainly not for all situations. So they are all local. And the same here, H star is something which is useful locally, meaning locally for particular classes of problems and not all problems that concerns leaves in trees, right? So this is very important. However, this class and its defining parameters cannot be determined by analyzing H star. So if you ask under which circumstances can I apply H star, he says you can't do it by analyzing H star, by just looking at, oh, this is interesting, how should they jump from one location to the other? That won't help. And there you see it, that's the same argument as in the argument with the free fall. You cannot determine where you can apply the law of free fall in realistic situations with air pressure and everything. You cannot apply that by analyzing what is the assumption, namely vacuum. You cannot, by knowing that, you don't know whether that's a good assumption for certain situations or not. You cannot determine it that way. The only way to determine that is by the implications, that namely the predictions. So this is the same here. If you analyze, then later it will be the case, if you analyze an economic hypothesis with counterfactual assumptions, you cannot find out under which circumstances this hypothesis will do well by analyzing the hypothesis itself and the counterfactual assumption. That won't give you that information. So this is what he's saying. This class and its defining parameters simply meaning how to characterize these classes in which you can apply H star successfully, cannot be gotten by analyzing H star itself. But you've got to do something else, namely look at the predictions. All right. So now example 3. Now we are coming again somewhat more close to economics. And the example here is an expert billiard player. And an expert billiard player, she behaves as if she calculated the trajectories of the billiard balls on the basics of the law of physics. So again, to say, if I describe the behavior of an expert billiard player and I want to predict what she's doing in the next next push of the ball, then if you calculate that, then you have a wonderful predictions for the behavior of that expert billiard player. This counterfactual analysis would give excellent predictive results concerning the shots performed by the expert player. This is what he's saying, right? Now, but the point is, of course, that you know that the expert billiards players don't sit down and solve the differential equations, and then calculate it, but they do it somehow from experience. Okay. So this is the example. This is a short step now, once you have digested that example, to example 4, which is one of the examples now, a real economic example. In a wide range of circumstances, firms behave as if they rationally maximize their expected returns on the basis of full information. Right? So this is the standard description of firms, right? They maximize their profits on the basis of full information, and we have fully transparent and working markets, and so on. You have many of these idealizing assumptions, and the agents are all rational, and so on and so forth. So this is very much the same as the expert billiard player example. This is what he's claiming. Now, the confidence in this counterfactual hypothesis, namely that the firms calculate everything, is not by empirical investigation of the behavior of businessmen or business people. The same as with the expert billiard player. When you say, how do you know that the behavior of the expert billiard player will be equivalent to someone who really calculates by solving the differential equations? You say, well, they're experts, and they will find the optimal solutions, and whatever way they do it, they will end up. Otherwise, they wouldn't be the experts, because they would be selected out. And that's the same with the firms. It's not an empirical investigation that the most successful firms are pretty close to the optimal value, how in their pricing policies, whatever they do, but it's just otherwise they find competition that is better than them, and then you get a process in which you find firms then behaving at the maximum. If firms behaved not equivalently to rational behavior, they would be wiped out by natural selection. That's the argument, right? So that's the same argument as in the tree case, right? The leaves really behave optimally because wouldn't they, or the whole tree as a whole, but wouldn't they have a competitor who'd find, or that would have found the optimal behavior, and then in the long run, selection would wipe them out, because it's always differential selection, and only the best ones survive, because there's always competition about water, sunlight, and everything. And most importantly, countless applications to specific problems and implications of the hypothesis are not contradicted by experience. This is the most important fact. He says, if you work in your analysis of firms on the basis of these counterfactual assumptions, this is this is how you get the best results empirically. This is the point. So in the end, it decides whether you get the best results, even if your counterfactual assumption, even if your assumptions are counterfactual, and that is the most important thing. And then, in addition, no widely accepted alternative exists. If you find, of course, a more realistic assumption that yields better predictions, then of course you'll take it. But if that doesn't exist, then you work with these more or less primitive, counterfactual, therefore deeply false assumptions. But if they give you the right results, then you are happy with them. Right? So the result is then in the examples, the assumptions of hypotheses are intentionally counterfactual and are as such incapable of direct empirical test. That's the point. Right? This is the point at what he's aiming at. And that, he thinks, holds true of all of economics, right? They contain intentionally counterfactual assumptions. These counterfactual assumptions are justified by some sort of arguments. We'll see more about that. But as such, they are incapable of direct empirical test. As you cannot directly empirical test when you have the air pressure case, you can measure the air pressure, but you can't say whether the assumption for the falling body, I assume vacuum, whether it's a good one or not. This is just impossible. Right? It just doesn't work. You have to only look at the predictions. This is what he's saying, and this is what he's trying to drive home with these examples. All right. So this was the point about the testing that, of assumptions, which he says in this, trying to show in these four examples, that these four examples contain intentionally contrafactual assumptions, and as such, they are of course not testable empirically, because they are counterfactual. You know they are wrong. Right? You can't test them. Right? Okay. And now the next, this is the next section then, is the significance and role of the assumptions of a theory. Again, you have the assumptions with scare quotes in the title. So this is very important. This is the core of this Milton Friedman's paper, is to understand what these counterfactual assumptions are doing. And also in the next section, we only talk about that. This is what he's trying to convey, and which is, I'm afraid to say, largely misunderstood in the literature. So what he's claiming then is that assumptions of a theory, these assumptions with scare quotes, play three different roles. They are an economic mode of describing or presenting a theory, that is dealing with in subsection A. Then they facilitate an indirect test of the hypothesis by its implication, that's subsection B. And they specify the conditions under which the theory is expected to be valid. This is a somewhat tricky formulation because the assumptions themselves do not do that. But you can, by looking at the assumption and then testing, then you can see the sort of situations for which the theory is applicable. And that's, of course, restricted by the assumptions. Take the law of free fall. It doesn't work in syrup, right? If you take a steel ball and you put it into syrup, the steel ball will fall down, but not according to law of free fall, because it falls down with constant velocity, because the friction is then the same as the gravitational force, and so it falls down with constant velocity. But of course, you can look at the assumption and then test. So it's from the assumptions and the predictions and so on, you get information about the conditions under which the theory is valid. All right. So we start with the use of assumptions in stating a theory. This is how he leads us through that. Okay. Now, the point is first that this is what he said earlier also, a hypothesis may be capable of summarizing many different situations by using an assumption. So he said the hypothesis in economics and everywhere else is something small that explains a lot. So, and in the assumption, there you get a sort of summarizing force that brings certain situations together, namely those for which the assumptions is then sort of valid or useful. And this is what the assumptions does by summarizing many different situations by using the assumption. And an example is again this counterfactual hypothesis about the distribution of leaves on a tree that summarizes many different situations, right? Many different kinds of trees, not all kinds of trees, but many kinds of trees, many topological situations from which you can say, yes, I can say something about the distribution of leaves by that counterfactual assumption, by saying each leaf moves individually to get the maximum sunlight out of the situation in which the tree is, right? This is what he means. So that counterfactual situation summarizes, focuses information about the behavior of trees. And more generally, that a hypothesis or theory asserts certain forces to be important for a certain class of phenomena, and by implication other forces to be negligible, and the mode of operation. So this is the idea when you have a hypothesis in economics then mostly, that you say for that particular situation not everything is relevant. It's only certain, he calls it forces in analogy to physics, that certain forces are relevant, and the hypothesis somehow gets these forces into focus and abstracts from the rest. So only what is really important for the situations. Economic examples will follow, cigarette industry. And the hypothesis consists of two parts then. The first is an abstract, what he calls an abstract model of the world, simpler than the real world by containing only forces asserted to be relevant. So if you have now a hypothesis both in physics, he thinks, and also in the social sciences, including economics, first you have an abstract model of the world. And the model itself has no vagueness or approximations. It's abstract and complete. And what he means is, you see again with the free fall example, the abstract model is we have the world with a vacuum and only constant gravitational force. Right? This is just an abstract model, as you find many of these abstract models in economics, of course. You write down 5 equations, and that's the model, right? And that's self-contained, it's mathematical, and then you can play around with the equations and find what solutions there are, what their qualitative properties or quantitative properties are. This is what he thinks here. We have an abstract model of the world, simpler than the real world, by containing the only forces asserted to be relevant. And then the second step that you need, because that's an abstract thing that has no direct connection to the world, you need a set of rules defining for which phenomena the model is intended and establishing correspondences between model and world. So in order to apply that, you got to know, so what do I do with that abstract model? And this is something, how to connect that with the world. This is what you need. And again, now he says something important, I think, for the practice of science. The rules of application must be incomplete. That's not a normative issue, but he says they are necessarily, unfortunately, incomplete because of the openness of the set of possible applications. So if you have, for instance, the law of free fall, then the rules under which you can that tell you for which situations you can apply it cannot be fully specified, because you may encounter situations which you don't have in mind yet, and then you see, oops, for these situations it's also applicable. So the rules give you an outline, give you examples how to apply it, and then you can apply them to particular situations. By the way, this is very similar to what Kuhn much later then says, well, 10 years later, says about the application of paradigms. It's something which you have to learn, and you learn it by examples, but it's not fully specifiable in rules. So it's an insight that's, I think, quite general. So the rules must be incomplete because of the openness of the set of possible applications, and are not completely sharp, leaving room for judgment. And then he also says something, I think, which is very important and very true. They can only be learned in the right scientific atmosphere. So if you ask yourself, why is there such a difference in the quality of education in universities, and why are such many labs, so wherever you go, whatever field you go, whether it's physics or biochemistry or whatever it is, why is it that people learn so much more in the really good labs? So why are people doing postdocs in the natural sciences, especially in the biomedical sciences, doing postdocs somewhere? Because they learn something in labs they cannot learn anywhere else, because it's not completely specifiable in rules. But you learn it, as he nicely says, in the right scientific atmosphere. You just learn by copying the masters. You just learn from them, you talk to them, and then you learn how the game is played. And the better the people are from which you learn, the better is your chances yourself to becoming very good. So this is why we need this apprenticeship also in science. He's describing that, that's absolutely right, because it's not fully codifiable. Right? It's not codified completely, but it's a sort of practice that you learn from the master. This is the situation, and he's absolutely right here, I think, because this is the way, how you learn from those people who work in economics now, who are the best with models. You learn from them how to design models and then how to apply them to real situations. This is what he's saying here. Okay? A simple example here is Euclidean geometry, as he believes again. Now he's testing us whether we know enough about Euclidean geometry. And he says abstract, there's first of all an abstract purely mathematical model. This is what is called mathematical geometry. If you do mathematics, so it's very different from what you learned in high school usually. If you do mathematics, mathematics has nothing to do with real space or anything like that. It's abstract. You just write down the axioms and then you prove theorems. And even the word, whether you speak of a plane or a line or point or whatever, you can replace that. That's unimportant. It's just what's in the axioms is important. And you have what is today called mathematical geometry. And if you want to use geometry for real space, then you've got to switch from mathematical geometry to what is called physical geometry, where you identify physical things with geometrical objects that cannot be completely described by rules again. So for instance, you define a straight line by a light ray, right? And then you say, okay, if the light ray describes in my space what is a straight line, but that if you use light rays, you don't know the geometry beforehand. You've got to find out. And this was what happened in the 19th century, that people found out, whoops, light rays could perhaps not only go in straight lines, and as you now know, of course, by the existence of black holes, light that tries to get out there doesn't go out in a straight line, but it can't go out in a straight line because it's trapped in the black hole. Therefore, the hole is black. It's not a hole, but anyway, it's black. Okay. So this is the example. It's how in physics geometry is used, because in mathematics itself, when mathematicians speak about spaces, forget about space. This is not our space, our three-dimensional space that surrounds us. It's very abstract. It's only what's in the axioms is really what the space is. So this is an example. Whether that's helpful or not is a different question. Anyway, But the free fall example, I think, is good enough that one thing is you write down the equation for free fall in which you assume constant gravity, or not assume, which is defined for constant gravity and vacuum. And then the question is, when I try to apply that to concrete situations, it's not one-to-one. I don't know at which cases, for which cases it's really suitable, and I got to find out. Then he says, in economics, so-called crucial assumptions are then the key elements of the abstract model. This is just an explanation how economists use the term crucial assumptions. Although a model can itself be described in many equivalent ways because axioms and theorems can change place, crucial assumptions are singled out for practical purposes. So what he's saying is that what economists call crucial assumptions is not something that's hit in stone because it's a part of the theory. Because if you look at the theory, you have a few axioms and consequences. As you know from mathematics, if you have certain theorems, then you can sometimes replace theorems by axioms if they are equivalent, right? So it's not a unique description of that abstract model. And therefore, what is a crucial assumption cannot be read off of the set of axioms or the set of theorems. But it's different. It's from the applications, you can say the crucial assumptions are those which do play a very important role for practical purposes. That's the idea. All right. Now, I finish with that one, then we make the break. Then the second thing is the use of assumption as an indirect test of theories. And I must admit, although I've treated now this paper many years and many weeks, I try to read it, I do not fully understand what he's doing in B, in that section, and I've tried, and I made formalization, and I tried, and I just don't fully understand it. I can say I gave up, I must say. In this difficult section, Friedman argues that assumptions can be used for subtle forms of indirect confirmation of a theory. The argument is based on the fact that in an axiomatic system, premises and conclusions may sometimes exchange their roles. However, as Friedman concedes, this sort of evidence is not conclusive, and this section is without consequences for the rest of the paper. So it's an additional way where he says how you can indirectly use assumptions as a test for the theory. But I must admit, I don't get the logics. I tried hard, I didn't get it. So if you've got a good idea how to understand that, I don't fully understand what's going on. And sometimes I thought it's completely inconsistent, but that I don't believe, but I just don't get it what it is. And therefore, I leave it out, and I can promise you it has no consequences for the rest of the paper.